Welcome back. So this was the responsibilities of the data link layer, the network layer and the transport layer. Moving on to the next higher layer, it is the session layer. Session layer is placed just before the presentation layer and above the transport layer. The session layer also adds its own header to the data which is sent down to it from the presentation layer. And session layer is basically like a dialog controller. There are certain processes for which the services of the second, third and fourth layer are not sufficient. There are many processes for which these services that the first four layers provide may not accomplish all that is required. So therein comes the session layer, and session layer permits processes to add these synchronizing pulses or the checkpoints. Now session layer is responsible for getting the two communicating systems into a dialogue. So it will establish the dialogue, it will maintain the dialogue and it will terminate the dialogue. And in between, if there is a break in the dialogue, then it is the responsibility of the session layer to restore the dialogue. Session layer also does some kind of token management. So this property or this function of the session layer prevents two devices start on a critical task simultaneously. So it will prevent that from happening, and it will make sure that only one device starts with a critical task, and if one has started, the other one waits for its turn, and this it manages with the help of a token. And then it does synchronization, which I had shown in my previous slide, that it permits the processes to add checkpoints. Checkpoints means that if you are downloading or you are communicating with a device which involves large amount of data, then it will help you in putting checkpoints. As when you are downloading something and something goes wrong, then you need not start from the scratch. Let me give you an example. Supposing you are downloading a file of 2000 pages, and now you can put these checkpoints after every 100 pages. Now you have downloaded page number 523, you have downloaded up to page number 523 and your system crashes. When you restart, the session layer will make you go back from page number 500, not back to 0, because you had put these synchronization pulses, you had put these checkpoints after every 100 pages. So session layer will make you repeat only 23 pages again, not from the scratch. This is a tremendous help, especially when you are downloading huge files, and this will prevent from you wasting your time, and it is a big functionality given by the session layer. The presentation layer is right above the session layer, and it is involved in the semantics and the syntax of a message. It adds its own header and it receives data directly from the application layer. Let's look at the functions. It is involved with the translation. Now every computer has a process running on it, and this process has data in the form of character strings, numbers and so on. But before you can transmit any kind of data, it has to be translated into a stream of bits, and every system will use its own encoding methods. You cannot kind of force one encoding method on millions of computers on the internet. Every system will choose its own way of converting data into a bit stream. So to ensure the interoperability of different encoding schemes, presentation layer uses a very simple rule. So everything coming from the application layer, and whatever format the system has chosen to convert this into a bit stream, is converted into a common format, and this common format is then transmitted. At the receiving end, this common format is again changed back into the preferred format of the receiving machine. And therefore, for networking, the independent encoding schemes of individual computers is not a setback. And this process is called translation, and this is provided by the presentation layer. Now, sometimes you are transmitting data which is sensitive or it is private. So, presentation layer provides encryption mechanisms where you can change your data, you can change the form of your data which cannot be understood by everyone, and then you can transmit this data. This process is called encryption. At the receiving end, you do the reverse and get back the original data, and that's called decryption. So, encryption, decryption protects sensitive data, and it helps in transmitting private data, and this is also done by the presentation layer. And one example I have written here, it's a very simple example. Supposing I am transmitting only text, but every A is replaced by the next alphabet. Every alphabet is replaced by the next alphabet. So, A will be replaced by B, B will be replaced by C, C will be replaced by D, and this is a very, very simple way to kind of code your data. And there are very many sophisticated mechanisms of encryption and decryption. The third functionality of the presentation layer is compression. Compression helps save bandwidth. You can send your data by much less number of bits than required. And this compression is especially useful in the context of multimedia like images, audio, video, and these things that I have mentioned below compression, which is MP3, JPEG, MPEG. These are popular compression techniques for audio, image, and video respectively. So, presentation layer provides translation, encryption, and compression of data. This is the topmost layer, the application layer. So, application layer gives user the access to the network. So, user can be a human being or it can be a program, but the user gets the access to the network layer via the application layer. Application layer will give you the user interface, and it will provide support to the various services that you take from the network. For instance, email services. You can also use directory services. So, these blue things that I have seen are the various services that we can use, and the interface of the user and the support for these services is provided by the application layer, and application layer passes the data as well as the header that it adds down to the presentation layer. There are many applications that are available on the internet at the moment. If I just mention some of them, there is this network virtual terminal which provides a software emulation of a physical terminal of a remote host to a user. So, user can be will be able to access a remotely located computer just sitting in his own office. It simulates the physical terminal of the remote host on his own machine, and it starts communicating with the host, and the host feels as if its own physical terminal is communicating with it. You have FTPs which give you this process of file transfers, file access, and file management on remote hosts. So, you can easily transfer your files, you can access them, you can retrieve them, you can store them, and this application is very useful for managing large files. All of us have been using the mail services. That's another very popular application. We are these days dependent on email so much. All of us use it at some point in time every day. Similarly, distributed databases are also available as directory services, and these are the kind of services that are provided to the user by the application layer. So this is the summary of layers. Physical layer, it transmits the bits over a medium and it gives us the mechanical and the electrical specifications. Data link layer organizes our data into frames and it provides a hop-to-hop delivery with certain amount of error and flow control. Network layer gives us the source to destination delivery and it also provides routing for internetworking. The transport layer provides reliable process to process message delivery and it also gives us end-to-end flow control and error control. The session layer is used to establish, manage and terminate sessions. Presentation layer gives us translation, encryption and compression of data, and to allow access to the network resources we need the application layer. So this is the summary of the OSI model with its layers. Now if we look at the TCP/IP protocol suite, then let me mention here that the TCP/IP protocol suite actually predates OSI. So it actually was developed before the OSI model. And the original TCP/IP protocol suite was defined as having 4 main layers: the application layer, the transport layer, the internet and the host to network layer. So in this way, if you really map the OSI with the TCP/IP, then it really does not exactly match the OSI model. As you can see, 3 layers seemingly are not present in TCP/IP. But if you start looking at the functionalities of the protocols in the TCP/IP protocol suite, then the link layer actually performs the functions of data link layer and the physical layer. So some of the books do divide the link layer into 2 and consider TCP/IP as a 5-layer model rather than a 4-layer model. So there is a little bit of an ambiguity between certain books. Some treat TCP/IP as a 4-layer model and some treat it as a 5-layer model. The difference being the link layer right at the bottom is sometimes combining the physical and the data link layer, and sometimes they are being treated as 2 separate layers. Now the first 4 layers in the TCP/IP protocol suite, they provide the physical standards, the network interfaces, the internetworking and the transport functions, and these exactly correspond to the functions that are provided by the first 4 layers of the OSI model. Now the 3 topmost layers in the OSI model, which is the session layer, presentation layer and the application layer, they are represented in the TCP/IP protocol suite by a single layer, and that is called the application layer. So in a way, application layer in the TCP/IP model combines the functionalities of the session, the presentation and the application layer, though some of the functionalities of the session layer are also done by the transport layer in the TCP/IP model. If I have to define the TCP/IP model, then I would call it as a hierarchical protocol made up of interactive modules, each of which is providing a specific functionality, though these modules are not necessarily interdependent. They are fairly dependent also. And if I have to define the OSI, then I would say the OSI model specifies which functions belong to each of its layers. The layers of the TCP/IP protocol suite, they contain relatively independent protocols. They can be mixed and matched, and that depends upon the requirements of the system for a particular application. This is now the real comparison of the TCP/IP and OSI model with the protocols that we use specifically under the TCP/IP architecture. So as I had said in my earlier lectures, OSI is thought to be made up of layers, and then you can choose the protocols for each layer. TCP/IP is usually considered as a stack of protocols, and these protocols are giving us functionalities which are analogous to the layers in the OSI model. And if you look in this diagram, on the left in the gray are the layers of the OSI model, starting from physical layer right up to application layer. And then these colored hierarchical structures are representing the TCP/IP model. Right at the bottom is the combination of the physical and the data link layer, and here Standard proprietary protocols can be used. No particular protocols are defined under the TCP/IP model. Any standard protocol which fulfills a requirement can be used, and generally LANs and WANs are the underlying networks in TCP/IP model. The internet layer is same as the network layer in the OSI model, and the internetworking protocol IP is the main protocol in the TCP/IP protocol suite. It performs all the functionalities that the network layer gives in the OSI model. IP is supported by certain other protocols like ARP, RARP, ICMP. These protocols help IP sometimes in getting the physical address mapping to logical address mapping, or logical address mapping to physical address mapping, or to report certain query messages, or there is some problem with the datagram on the route and you have to communicate to the source. So these supporting protocols help in the datagram delivery by the IP. Transport layer maps with the transport layer of the OSI, and there are three main protocols that the TCP/IP model supports. SCTP, which is relatively a newer protocol and supports the voice over IP, stream control transport protocol. TCP is a very popular connection oriented protocol, and UDP is a connection less protocol in the TCP/IP protocol suite. We'll of course be doing these layers in greater detail, and we'll understand each of these protocols very soon. Application layer is also showing the various services that are provided to the user, and there are many more. And as you can see that the application layer is combining the session, presentation and application layer of the OSI model. So this diagram kinds of compares and contrasts the TCP/IP protocol suite with the OSI model. Now when I was explaining the various layers, these are the four kinds of addresses that I mentioned, the four kinds of identifiers that I mentioned. I'll give you a quick recap. Data link layer was talking about physical addressing. The header of the data link layer was adding bits which was identifying the sender and the destination from hop to hop, and this was at a local environment. It was under a local jurisdiction, and these are called physical addresses. Then I mentioned another identifier at the network layer level, and these were called logical addresses. And logical addresses are such that every node, every device on an internetwork will be unique by virtue of a logical address. The physical address is unique only within a network, but when you cross a network boundary, then the physical address is no longer unique. So if the communication is happening locally within a network, the physical addresses suffice. But if you start communicating with hosts that are not located on your network, then you need logical addresses. I had also mentioned port addresses, which is at the transport layer level. These were those identifiers which bind incoming and outgoing messages to a particular process running on the host and the destination machines. And these are given to every process by the transport layer. At the application layer also you have some kind of addressing, and that's called as specific addresses. For instance, I type an email, but I have to send it to somebody, and this email is originating from me. So I have an email ID and I send it to a specific person who also has a unique email ID. So those will be called as specific addresses. Now the physical addresses are usually 48-bit data, and this 48-bit data is contained in the header of the data link layer. The logical addresses at the moment is using IP version 4, and these are 32-bit addresses. So the header of the network layer will contain 32 bits of the source and 32 bits of the destination address. The port addresses are 16 bits, and these identifiers are generated by the transport layer every time the process opens up and requests for communication. There will be a port address for the source process and there will be a port address for the destination process, and it is 16 bits will be there in the header of the transport layer amongst many other things. The physical addresses, the logical addresses and the port addresses are very, very important, and they each offer identification to the source and the destination. Sometimes you combine the logical address with the port address and it is called as the socket address. So you put 32 bits of logical address followed by 16 bits of port address, and this forms the socket address. So let's see how and where these addresses are located. As you can see, the physical addresses reside in the data link layer. So if it is the OSI model, it is specifically there in the data link layer, and if it is a TCP IP model, then it is in the first layer. It is in the first layer which is combining the two functions. And in this the TCP IP is explained as a 4-layer model. You can also segregate the two layers into physical and data link layer, then the physical addresses will be in the data link layer. Logical addresses you can see is in the network layer of both TCP IP as well as OSI. The port addresses are also there in the transport layer of both models, and similarly the specific addresses are there in the application layer of both the processes. So this is the comparison of the various addressing mechanisms that the OSI model or the TCP IP model will use. Now I will show you one example where a process is communicating with a process on a destination machine. You can see the two computers, A is the sender, B is the destination. 3 processes are open on each of these. But the first process on A is communicating with the first process on B. Now the data originates from the user. So user can be a human being, it can be a software, but data has to be initiated by a user. Now once the data is created, it will be handed over to the application layer because it is going to use the services of the application layer. So supposing, let's assume this process is using a email. It is using the mail services, and there is an email written which has to be sent to the machine at P. Now this email will go down to application layer using SMTP or some similar service provider. This data goes down to the transport layer. So the moment we do not see a specific session layer and a presentation layer, we know it is following the TCP IP protocol suite. Whatever were the services that were being provided with by the presentation and the session layer, they have been provided by the application layer here. Now when the data comes down to the transport layer, you can see that there are 2 identifiers as the header, A and J. So A and J are showing us the processes that are going to communicate on A and P. So the process A on A is going to communicate on process J on P. So those identifiers are kind of the port addresses which the transport layer has added in its header. Now A, J and the data together becomes the segment which goes down to the network layer from the transport layer. Now transport layer will manage the process to process delivery. Whatever data comes from that process on A to P and whatever comes back from P to A for this process will be maintained as a complete tube-like structure by the transport layer. It will not get mixed up with the other processes that are open on these machines. As you can see, the network layer does not know about the port addresses. It just adds its own addressing mechanism, and it has added the logical address of A and P, which is a 32-bit scheme, and that is shown in its header. Header contains other informations also, but these are definitely there. So you have the logical addresses of the source and the destination, which is part of the header by the network layer. You have A and J as the header of the transport layer, which is identifying the processes that are opened on each of these computers, and then the network layer will pass down its packet to the data link layer. And you can see that the data link layer will not touch APAJ, the headers of the network layer or the transport layer. It will add its own header and trailer. Please note that the trailer is added only by the data link layer. Trailer is not added by any other layer. The header of the data link layer now will also contain the physical addressing. So if the machine P is located on the same network, it becomes so much easier. The other layers, probably the network layer addressing, may not be used. But if this packet is going to cross an interface, it's going to go to another network, then the data link layer will contain the physical address of that connecting device, which is connecting the device on this particular network to the network on which your destination resides. And then this now encapsulated data link layer frame is sent onto the internetwork by the physical layer in the form of Roberts. And a similar analogous process is happening on the destination. As you can see, at each layer the headers are read and removed, and whatever information those headers were supposed to give, error control, flow control, framing, identification, all those are read at that particular layer, and then the encapsulation part of the data is passed on to the upper layer till it finally reaches the desired process. So this is how communication happens over a OSI model or a TCP/IP model, and this broadly gives us an overview of the distinction between the two reference models. We stop here and we will continue with some different sessions in times to come. Thank you.